I'm really happy to be here in Los Angeles, so thanks for the organizers. I think Jörg, Mira, Jürgen, whoever recommended me for attending the whole period. I'm really happy and really excited to finally start engaging in all the group discussions. And today I will present mostly about continuum modeling. That's what I was working on during PhD and postdoc time, and I kind of continued this through the first years of my career. And I will also do this so that I can introduce a little bit of theory, because I think the presentation should involve a little bit of tutorial-like guidance to the topics as well. So I try to give you some guidance like that in addition to showing you the research. So I really like this long program because it kind of tries to tackle all the different scales of electrochemistry, from the material side to the interface to the multi-scale modeling side, and that's exactly what we are trying to do as a group. So our group is divided into 3 different parts, and the first part of the group deals usually with materials and their properties, the reactions, electrochemical reactions that happens on these electrodes, how the structure of the electrodes changes, and all of that under the conditions that we usually have in electrochemical systems. And the second part of my group, I'm trying to more in detail understand how the structure of these interfaces looks like atomistically. And then we have another group which focuses more on the multi-scale part. And today I will mostly focus on this material part. Maybe there will be another opportunity in this program for me to present some other results. But today I will put the most focus on this part. So when we want to simulate electrochemistry, we need to simulate interfaces. I think that's pretty clear from this program so far. So we need to simulate this whole thing, the solid and the electrolyte. And if we do DFT, we usually have only access to a small part of that. So theoretically, what we need to do is we need to use the right boundary conditions, obviously, and we need to charge up our system. And we need to treat the electrons grand-canonically, as well as the ions which come in and out. And in principle also the catalyst atoms, but often we treat them still canonically. And then we can construct a grand-canonical potential to treat this interface, which consists of the free energy and these chemical potentials, electrochemical potentials. So that's the idea behind it. The question is how we can do this in practice, right? How can we simulate this? So first of all, once we do this, what we do is something like an equation of state, right? That's what we are supposed to get. So we should get a relationship between the electron number and the electron electrochemical potential. That's our equation of state. And we can also formulate it using intensive variables. Then we have the surface charge density here. And then we can relate it like that. And we can also do something like this. We can do a Taylor expansion of this electrochemical potential of the electron around the potential of zero charge, which is the point where there is no surface charge, so no excess charge on the surface. So and if we do this, then we get something like this here. You can see at the potential of zero charge, we have this electrochemical potential, then we have a linear term, which is basically with the inverse capacitance, and then we have higher order terms, which represent the potential dependence of the capacitance, right? So we can write down this equation of state, and we can approximate it, and the capacitance will then be, if we write it down correctly, it will simply be the derivative of the surface charge density with respect to the electrostatic potential. And that will be potential dependent, right? So we can evaluate the derivative at the PCC, then we get the C0 here. So this is the formulation of the properties that we actually want to get, right? So the question is, how can we get it? And now we have the full Monty of computational methods, and during this workshop we saw all kind of methods already, I think. I think we actually saw all of them, maybe. So we can do the AMD level, of course, which is very accurate, but way too expensive to sample ion dynamics usually, which are on a much slower time scale. We can use force fields, so we can do something like QMMM, where we then sample the electrolyte with force fields. The sampling will become much more efficient, so we can actually resolve all these distributions of species. But we also have the problem that we need to parameterize this force field, the classical force field, for every single system. So we have a problem with transferability. What we can also do is we can use these solvent distribution models, or rhythm, or density functional theory for liquids. Then we can actually get these the distributions of the solvent molecules, really these oscillative functions. But we have the same problem actually as in the classical force fields. We will introduce a lot of parameters which we need to determine for every particular system. And we can further coarse-grain, and we come to the implicit level. So here we represent the electrolyte fully as a dielectric continuum. And the big advantage here is that we actually end up with methods which are very transferable, but of course under the cost of accuracy, right? The question is, can they still be useful for us? So first, let's look at how we actually construct. Oh, you have a question today.
Can I stop you a second? So why do you say that the solvent distribution is not implicit? I mean,
it's kind
you're solving for a field, right?
There are these methods molecules. Like rhythm. They are more like classical force fields, right? Because you parameterize all the like Lennard-Jones parameters and everything, and then you do the equilibrium approximation. So I would say there are models which are more close to force fields and some which are more close to implicit, right? I just put them in general like that, but there are, somewhere in the middle.
Do you see it like if you look at the classical density functional theories?
That would be probably more close to the continuum.
Do you think they have a transferability problem?
They still involve parameters, right? But they might be, because they are more close to the continuum side, I think they will be a bit better with transferability. So usually, the more atomistic details you include, the more you lose the transferability, right? Because you have to parameterize all the interactions with the surface, with the quantum chemical part. So that's you kind of get more details, but you lose the transferability. That's kind of the take home, I think. And then for the continuum modes, what we generally do is we construct a free energy functional. So in DFT, we have these regular parts here. I wrote it down as a function of density alone, just for simplicity. Of course, in practice, we do Cohen-Sham, but just for simplicity, I wrote everything with rho. And then we have here the kinetic energy of electrons, the exchange correlation functional. We have the electrostatic energy, the mean field electrostatic energy, and then we have some kind of non-mean field contributions. And the mean field electrostatic energy of the system is given based on the electric field and the polarization functional, which we need to choose. So I will show you in a minute how we can choose it. So that we can actually now change to control our implicit environment. And then we have non-mean field contribution, and here we can add all kind of things that we want to make this purely electrostatic model more realistic to represent our environment. So we can add cavitation energies, we can add ion effects in the electrolyte, dispersion or water rotational contributions. And then we just do the minimization with rho, we get the Cohen-Sham equation. Minimization with potential, we get the generalized Poisson equation. So in practice, we need to solve these two equations iteratively. So for the polarization, so we then have this generalized Poisson equation, which comes from the minimization. And we have E plus P equals this total charge density. And the P, we can use an electronic polarization. We usually use, in most models, a linear response ansatz for that. So this depends linearly on the electric field. And then we have a dielectric function here, which we parameterize in a very simplified form. Usually we use a step function for that as a function of the electronic density. So most models use these linear local models, which use isotropic, frequency-independent, local dielectric functions. But there are also other models, for example, the one Craig implemented, which then add rotational polarization to that. And these are the nonlinear functions of the electric field, so you can get nonlinearity into there. Okay, and for the ionic charge density, then we can also make different approximations. So we can, all kind of things we can do. We can add a planar countercharge. We can add a linearized Poisson-Boltzmann model, a Poisson-Boltzmann model, modified Poisson-Boltzmann, and so on. So many different levels of theory, which can all relate to different choices of free energy functionals. Then the question is, what should we actually use, right, when we do the calculations? Well, in practice, we see the capacitance should look like this, right, this double hump here. But then, do we always need such a complex model? And we can do the trial, and we can take the linear local models like this for the dielectric. And then we can say, let's try out different ionic models. And then we can categorize them into models which give a constant capacitance as a function of potential. This is, for example, the linearized Poisson-Boltzmann model or the planar countercharge model. And there are models which give a variable capacitance, which is the Poisson-Boltzmann or size-modified Poisson-Boltzmann model. And well, when we look into some different models here, then we can see if we use a constant capacitance model, they are usually constant here. Oh, this should be CCM, I think. Yeah. I know this is the variable capacitance. The green one and the red one, these are constant capacitance models. So the capacitance is almost not changing. And for the others, we can get these variations here. But the problem is that we don't really know the correct model. And also, we don't know the correct parameters. So when we introduce more complexity, we have to parameterize these things. And in the end, the only reference data we have is the experimental capacitance. So the question is, how much complexity do we want these models for now? And indeed, when we do electrocatalysis, we are often under like highly biased conditions. So we are, for example, here, if we look here at this curve, we are at like minus 1.6 or something like that. So we are in the region where the capacitance is actually constant. So if we use a constant capacitance, we don't do too much error in estimating the charge. We only neglect basically these oscillations close to the PCC. So in practice, it turns out that for electrocatalysis, often using constant capacitance is not too bad of an approximation. And that brings the advantage of making these models much more simple. We can also then formulate simple models for the energies. So for example, we can look into the change of the energy with the number of electrons. This is actually the electrochemical potential, which we expressed as a Taylor expansion before. And then we can integrate this. Then we get a quadratic equation of the surface charge density. I put these remaining terms here. And that means that when we use a constant capacitance model, we would expect a parabolic dependence of the energy on surface charge density. And when we then calculate the Grand-canonical energy from this, then this one was this quadratic form. And we need to reformulate all of this a little bit by inserting this equation of state. And then we end up with a parabolic equation again, this time in the potential. Okay, so for the constant capacitance models, we always expect a parabolic shape of the energy, the grand-canonical energy as a function of the potential. And this means that we have only two parameters here which influence our behavior. One is the capacitance at the PCC, the other one is the PCC itself. So it makes things much, much simpler. We only need to, once we have these parameters, we don't need to calculate any more potentials. We can fit this using just 3 data points, right? Another thing that is important here is that when we now actually calculate relative energies, for example, what we are often interested in is adsorption energies, and we calculate them in the thermodynamic low coverage limit, then we often see that, then we generally see that the constant charge or constant potential energy differences are exactly the same. That's what we expect, right? In the thermodynamic limit, it doesn't matter what we keep constant, the charge or the potential.
Sorry, I don't understand. What is thermodynamic low coverage limit?
So for adsorption,
dependent on the parameters, you can also have high coverages in thermodynamic.
That's right. That's right. So I'm specifically referring to like adsorption. Okay, yeah, that's true actually. So I think this limit would be. Yeah, because I looked usually into the low coverage, but I think it's generally valid. I mean, in the thermodynamic limit, they should always be the same.
Halide adsorption metals, they have always high coverage.
Right. I mean, in the thermodynamic limit, they should always be the same. It doesn't matter if you have high or low coverage. Yeah. But my examples were kind of for the low coverage, but yeah, there was actually even some other papers from Georg Kastlonger, and he also showed in thermodynamic limit, you can actually show these expressions to become the same. Yeah. By the way, how long do I have in total?
50 minutes.
50 minutes, including questions, right?
No. 50 minutes plus 50 plus 10.
Oh, okay, great.
So if you look at this one at 3:20, I will get up.
Okay, good. I just need to roughly plan it, okay, in my head. Okay, great. So I just want to illustrate you shortly what these two methods really do. So in the computational hydrogen electrode picture, which people used before all these implicit solvation models popped up, people don't actually include at the electrolyte at all. So what they do is they just take the surface and they put the adsorbate on it like hydrogen. And then what this essentially means is that their work function, the Fermi level, will shift, and they will simulate everything at 0 charge, and then they calculate the reaction energy, right? Now, what this grand-canonical method with implicit solvent does now is it corrects 2 things. So first of all, starting from this, what it will do is it will try to correct out this surface dipole change due to the adsorbate by adding extra charge here to the surface. So if you add this extra electrons here, then you can compensate the dipole and you can match the Fermi level. So you can restore constant potential conditions by shifting one of these states by the corresponding amount of charge. So this is what we call charge equilibration usually. And we can also then go ahead and we can change the total number of electrons in these 2 states so that we can actually charge up the surface. So we can tune the Fermi level absolutely, right? So we have 2 steps, charge equilibration and surface charging, and this formulation includes them both. Now, if we do this the constant charge way, then actually we do only one thing. We only shift them both by a constant, so we add n electrons to both to shift them to a different potential, but they still have different Fermi levels, right? The point is only if your supercells are large enough, this different Fermi level doesn't matter at all, because, if you look at this difference here, here we are looking at n plus delta that you're adding here. We are adding n plus 1 delta, right? This 1 comes from the charge equilibration. So the difference between this and this method is that we are adding 1 more electron here for equilibrating the charge. And 1 becomes very small against n if n becomes large, right? So if your cell becomes very large, the supercell becomes very large, then the n will become large against 1, so it's just n, and that means the two methods will exactly give the same result, right? So if you want to use these kind of methods, generally the constant charge would be one way you could do it, but you just need to verify that these charge equilibration effects are negligible in the supercell size that you're using. So these are the expressions that you can then derive. I don't show you the derivation. So this is the potential and field dependence for these two methods, specifically written down. But what I just want to stress here is that you have these two different ways that the environment enters. One is via the dielectric function. The other one is via the ionic charge density, right? The dielectric function mostly modifies the potential of zero charge. It also modifies the capacitance. But the potential of zero charge is actually only a function of the solvation model. It's not a function of the ion model, right? So this means that the PCC is actually something we can usually control a little bit better, because we only need to make sure that the solvation model is reasonable. And it turns out that in the constant potential method, the PCC enters here everywhere in the linear and quadratic term. But in the constant charge method, you can see that the linear term is only a function of the PCC. The capacitance is fully sorted out to the second order term. Now, why is this important? Because the capacitance is much more complicated. It depends on the whole EDL model, the electric double layer model that you're using. But when you use a constant potential method, it affects the dependence on potential already to linear order, while on the constant charge, it affects it only in the quadratic order. And this means that the constant charge calculations are much less sensitive to your EDL model. So you can use various different ionic charge models, and you will get roughly the same dependence on charge. Then where is this ionic charge dependence? Well, it's fully in this equation of state, right? Because when you convert the sigma to the potential, then you have here your capacitance. So you basically fully sorted out this complexity of the electric double layer, and you moved it into the equation of state. Now, this advantage of this one is that you can use other ways to get the equation of state. You can use experimental data, you can use AMD, force fields, continuum models, which only focus on the equation of state. So that's actually a big advantage here. And you can focus your DFT calculations fully on this part here. And you don't need to mind using a very simplistic model of the double layer here. So that is why in most works we do, we actually use this constant charge method. And one work we did here that was actually still during my postdoc, where we looked into CO2 reduction, electrochemical CO2 reduction. And we first put CO2 on a surface, and we looked at how does the CO2 absorption energy change when we tune the surface charge density. So this is constant charge calculation of the adsorption energy. And you can see it varies very drastically. That's because there's a strong interfacial dipole. And it's actually roughly linear over a very long region, right? So this means that you will get the same kind of trend even if you use MPB model, constant charge, planar countercharge model. It doesn't matter. All these models will give you a similar dependence. So this gives you your delta G of sigma. Then the only thing missing is the sigma of u, the equation of state. And if you want to get some more sensitivity in here, for example, you want to resolve cation size effects, well, then you need a model which can predict cation size effects. So in this case, we used a modified Poisson-Boltzmann model, which can do that. And then you can plot the surface charge density as a function of cation radius and PCC. And you can see that both are parameters here to tune the interfacial electric field. So ultimately, when the cation radius becomes smaller, then you increase the electric field because you have more cations at the interface. And also, if you shift the PCC more positively, you increase the amount of charge on the surface. So that means you can actually now calculate the adsorption energy as a function of cation size directly. And we can also then estimate the activity, electrocatalytic activity for CO2 reduction, because CO2 adsorption is actually the rate limiting step. And that's what we did here. So we plotted here the CO production current normalized to lithium. And you can see how it is increasing when we decrease the cation size, because we stabilize more and more cations at the interface. And the dots here are the experimental data, and the lines are the theoretical predictions. And they were very well matched, especially also the facet trends, which come from the different PCCs. We could also even reproduce the frequency shifts with cation radius with the spectroscopic data. Now, this was all some time ago already, and then I actually decided let's do a model for the whole process, a proper model for the CO2 reduction process from CO2 to CO, and let's construct a kinetic model for that. And let's try to see if we can use that model to find a better catalyst for this reaction. I was also interested in, of course, how strong these ideal effects will be, and how will they affect which catalyst performs best for this reaction. So I went ahead and calculated all these energies as a function of charge. So you have all these charge-dependent energies, and only considering the linear term here, because the quadratic term is usually not that significant. I used here the surface charge, linear surface charge relation, equation of state. So a simple plate capacitor model in this case to estimate the surface charge. Then we have to add the terms from the computational hydrogen electrodes. So when we have from here CO2 adsorbs, and then we have a proton-coupled electron transfer. So we need to express the electrochemical potential of electrons and protons. And we can do this using the computational hydrogen electrode. Then we have here this EU plus 0.059 times pH terms in there. And then we do the kinetic energy barriers, and just used here the Brunstad-Evans-Polanyi scaling relations. So we just take the thermodynamic driving force and multiply it with the scaling factor, and everything is referenced to the reversible potential of each step. Okay, so this is the basic model. Now, if we use a model like this, then we have a number of parameters we need to calculate from DFT. First, we have these adsorption energies. Then we have these charge dependencies. And we have also the PCC. And we also, in principle, have these kinetic coefficients, but they are really difficult to calculate. We don't really have a good method for that, I think, yet for electrochemistry. So far, I used some rationalization based on the experimental results to choose them, which you can find in this paper. And then that means we end up with like 7 parameters. And the first thing to do is to try to reduce the dimensionality, because if we want to predict a better catalyst, we cannot calculate for every candidate all these parameters. So before that, we can see that this PCC is actually directly related to the Fermi level via this relation. There's a constant shift here, which we can obtain. So the PCC and the Fermi level are kind of equivalent to use in this context. And then to reduce the dimensionality, I just correlated all these properties with descriptors. So first, the common descriptor for CO2 reduction is the CO adsorption energy. So for various transition metal surfaces, calculated the CO adsorption energy and calculated the relation of these 7 parameters, six parameters with the descriptor. And you can see that the scaling is not perfect. Here for the adsorption, they scale quite well with the CO adsorption energy. But when you go to the charge sensitivity parameters, they have a very bad scaling. Now, when you move to the, when you include, however, the Fermi level into the regression model, so you have a two-dimensional regression model now, CO adsorption G and the Fermi level, then you can see suddenly everything becomes perfect. And the explanation is that when you want to describe these charge sensitivity, you need to have some information about how easy it is to transfer an electron from the metal surface. And the descriptor for that is the Fermi level. So the adsorption G of CO doesn't tell you much about that because it's usually mostly a covalent bonding effect, which is more related to the hybridization of the orbitals. So once you include a covalent and ionic bonding effect, then you can well describe all the parameters. And then you can go ahead and construct an activity volcano as a function of PCC and CO adsorption G. And you can pinpoint the position where you find the most active catalyst. And surprisingly, we found copper here, which was a bit surprising because copper is usually known to give reduced products, not CO. Copper is usually known to produce C2 and C1 products and so on, while gold is usually considered to be the most active catalyst. You can see in the original volcano, gold was actually more active, but now copper is more active. And the reason for that is this curvature here, which you get due to the surface charging effects, which give you this huge dependence on the potential of zero charge. So the surface charging effects are really important here to find the best catalyst. If you would only go by the CO adsorption G descriptor, you would end up with the wrong catalyst and predict the wrong catalyst to be active.
I'm a little bit confused. You might be aware of the work of Jan Rossmeisel, where they also look at CO2 reduction.
Yes,
they say there's copper is of course the number one because to at least to get hydrocarbons.
For hydrocarbons, yeah, for hydrocarbons it's the best. But for CO, I mean, people thought that for CO it's not. But actually for CO it's hard to say because CO could further reabsorb and reduce further. And actually this work kind of suggests that copper is actually a really good catalyst for producing CO, which might indicate that CO is actually reabsorbed and then reduces further. So that's also something we are now integrating in all our models, and which people have suggested, that CO is mostly then reabsorbed to the surface. Yeah. Yeah, so this model we can then also use, and we can actually put in all the experimental selectivity. So on copper, as I said, we get usually these C1 or C2 products like ethylene, ethanol, methane. And we have here the block which produces carbon monoxide, formaldehyde, and hydrogen. And we can see that this descriptor splits them very nicely into regions, which means it can be used as a good descriptor of selectivity. And we can also see that when we look into the block of copper facets, then we can also see that they form some kind of volcano-like trend as a function of this descriptor, which also is related to the fact that the rate-limiting step here is also the CC coupling, which is also driven by the electric double layer. So this seemed all very nice, and it seems to work. But so far, it's all bare transition methods. So the question is, of course, does this work for more complicated systems? So we worked with a group of GNO in KAIST to look into alloys. And the first thing they did is actually they looked into my paper and they said, okay, if this is true, let's take a ternary alloy and let's make exactly these conditions. The same CO adsorption as copper, the same PCC as copper. And that's what they did. So these two have exactly the same PCC and the deep end center as copper. But as you see, the selectivity is completely different than copper. Copper gives C1 plus products. They don't give it. They still give CO and hydrogen, and actually also formic acid. So this was, of course, in some way disappointing because it seems that reality is much more complicated than for these bare transition methods. But we then went ahead and we did all these charge-dependent free energy pathway calculations. And what my student, Xing-Chan Han, he actually found is that there are different pathways of deactivation for C2 plus product formation. For example, if we have a pure silver catalyst, then usually CO2 adsorption is very slow and will limit us to get a higher reduction rate. When we look into gold, then usually CO desorption is very easy, very facile. Actually, CO desorption is also a problem for silver as well. So all of these, they cannot hold CO on the surface. So CO will just desorb so that it cannot actually further reduce. Now we can try to introduce palladium, but pure palladium will have the problem that it binds CO too strongly, so the CO coupling step will be very difficult. And then in the middle, we actually have also CO desorbing usually, because CO can just jump to the next side and desorb. And also CC coupling could be limiting as well. So from running a lot of different configurations, we found that always one of these steps will happen, so that it's not possible to combine these alloys in a way that you can actually reproduce copper. So copper is still kind of unique in forming these C2 plus products. So in the second project, we then said, okay, copper is the best still. We cannot compete with it, so let's try to at least improve it. So in this project, we then added a lot of alloying metals to copper. And then we found actually that it correlated quite reasonable with the D-band center. I don't say well. I mean, it's still reasonable, I think, because the data, the amount of data, experimental data that goes in here is like really huge and really special, I think, in electrocatalysis to see so much data. So we still found some kind of correlation with the D-band center and the adsorption of that rate limiting step. So this correlation suggests that there is some hope to find some simplified descriptors for specific systems. Okay, so this was just to shortly give you an idea of how this performs in practice. But now I want to come back to theory. So far I always worked with these very simplified surfaces. So obviously the thing that we should do to move closer to reality is we should look into the active sites. What kind of active sites do we have on the surface? How do they evolve as a function of electrochemical conditions? And that's actually what we are now looking into a lot. So a recent work of my student, we were looking into copper facets. And the first thing we did is we calculated a lot of capacitances with different coverages of adsorbates. And we found the capacitance to be mostly constant in most cases. So this was, constant with the coverage of the adsorbates. So it seemed to be a good approximation to just use a constant capacitance for all the different configurations. Now, why is this important? Well, if you do these calculations, you need to do charge calculations, which are really expensive because you need at least 3 calculations to fit this parabolic curve. And charge calculations are also expensive. So you rather want to avoid it. But if the capacitance is constant, you don't need charge calculations. You only need to calculate the PCC, which you can calculate from your without any charge. So this is what we then decided for, even though we found some cases where we did find some capacitance variations, like O and OH. For simplicity, we decided to use a constant capacitance. And then what we can do is we can formulate the grand potential for the system. So this is an example for n hydrogen atoms adsorbed to copper 1-on-1. So then we have this free energy here. We have this quadratic term, which I showed you before. And then we have here the computational hydrogen electrode, chemical potentials. We can then also convert this to the SHE scale. This is the absolute electrochemical potential, but we can convert this to a standard hydrogen electrode voltage, because this is just a difference, so we can convert it easily. And then we have here also the U versus SHE. And once you convert this to the RHE, then you can actually see that there's, yeah, so if you, okay, well, look at this one again. So here, there's actually the pH dependence here. Oh, why is there the pH? Ah, yeah, here should be the pH, but yeah, right. Okay, sorry, here the pH is here. Everything depends on pH. But when you look into this equation, actually this computational hydrogen electrode part doesn't depend on pH anymore. But now the pH dependence is fully in this charging term, right? So what this means is that if you find any pH dependence here on an RG scale, it's fully due to charging, right? Or in other words, if you see any change in the stability, relative stability, at fixed voltage versus RG as a function of pH, it's fully due to charging effects. So that's why we often plot this as a function of RG, because it's simpler to identify the electric AA effects. And then with this, we calculate the surface tension and we plot as a function of voltage and pH. And we have always these slightly parabolic lines, and we connect the most stable phases to construct the kind of convex hull for each facet. And then we get a lot of data. So for each of the copper facets, different conditions, we find Pobe diagrams, so the most stable surface configurations. And what you can easily see here is that when we go to the oxidizing conditions, we have usually O or OH on the surface. And you can see that we have a lot of non-horizontal lines, which indicate electric AA effects. So the surface phase transitions are really strongly affected by electric AA effects. And that's mostly due to the hydroxyl on the surface, which has a strong dipole response. But when we go to the reducing conditions, we see a bit less electric AA effects. So hydrogen and CO are usually on the surface, and they are not that much sensitive. But we do see a lot of different differences with the copper facet. And we can then also go ahead and we can calculate the area ratio of the different facets to find out the shape of the nanoparticle. And we can see, interestingly, we still have to investigate this more, but we saw that the 111 facet is more stable only if we go to reducing conditions. Then it's usually covered by hydrogen. But in the intermediate voltage region, we actually saw the 211 facet to pop up, which was quite surprising for us, with hydroxyl coverage. So hydroxyl was able to stabilize the 211 surface substantially. And then when we go to the oxidizing conditions, the 100 becomes stable because copper 2O is usually 100 terminated. So when we oxidize it, it will eventually become a 100 terminated crystal. So this is what we found. So this is purely thermodynamically. And this is all based on the copper crystal. So the next step is to now fully look into all the configurational phase space of this crystal. And in order to do this, we have another project in which I just want to show very shortly to you, where we also use machine learning. And here we are then also, we are looking at the bulk at the moment. We also moved now to the surface, but I show you the results for the bulk. So we trained a mace potential on reduced copper oxides. And I wanted to understand the process of reduction. So when this copper 2O or copper O crystal reduces, how does the surface structure really change when we look at that? The reason for that is that people found that different oxides, they give very different electrocatalytic properties. So we first went ahead and we used a genetic algorithm for the geometry relaxation. But we actually found that we always get layered structures when we reduce the copper. And then we decided, okay, let's not use any genetic algorithm because it's not efficient to find these layered structures. And we just made all possible kind of layered structures. And then we were able to construct a convex hull between copper 2 and copper. And you can see that they line up almost perfectly along the convex hull. These are all layered interfacial structures. And they are all metastable. They are very close to the convex hull. So now with this, we are planning to explore the kinetic profile of copper reduction, which will enable us to identify metastable copper oxide structures. And then, of course, the next step will be, again, to look at that surface stability to understand the active site distribution. Okay, now I have, I think, 5 minutes left. So let me just very quickly show you something about the other works we are doing in the group. So far, I focused fully on the material side, where we usually use implicit solvent models. But implicit solvent models obviously cannot give us any accurate information about the interface. So what we have been also doing in collaboration with the Institute for Basic Science with Mining Zhou was to construct a machine learning potential. That's actually what my postdoc, Dianwei Hu, did. So we were looking into the interface of water and graphene here. And he constructed a machine learning potential to understand the orientation of water. And there was some experimental data available which showed that when we add more and more graphene layers, at some point there's another peak popping up in the some frequency generation spectra, which corresponds to hydrophobic water, to water which is not oriented H down, but which is lying flat on the surface. So we wanted to understand this. And the claim in this paper was that graphene is transparent, wetting transparent. So the substrate is actually influencing the orientation through the graphene, and graphene doesn't affect it at all. And interestingly, from the machine learning potential in SFG simulations, we found this to be not true. At least our simulations predict that no matter how many layers we have, we always have this second peak here, even with one layer. So then we thought, okay, so why with one layer we already have this peak, which actually indicates hydrophobic and hydrophilic water. And then we thought, okay, the calcium fluoride is very hydrophilic, so let's put a couple of water molecules here. And indeed, if you do that, and you see that the second peak actually goes away, this is because there's a cancellation of the two different signals. One with a hydrogen oriented like this and the other one oriented like this. So they cancel each other out with this water and this water. And then eventually this peak is gone. And we also calculated thermodynamic stability of water. And indeed, water is quite stable here. But when you start adding more layers, thermodynamic stability of water here becomes very lower than compared to the bulk, so that the water basically is pushed out of the surface due to the hydrophobicity of the graphene. So our current interpretation of the results is that for a couple of layers, there's water in between, and that leads to this cancellation of signals. Graphene is still hydrophobic, it's always hydrophobic. But when we add more layers, the graphene becomes more hydrophobic and will push out the water, which leads to this change in the signal. So these are the things that we can now explore with machine learning potentials, and we are also working hard on going beyond this. So mostly actually in this area, we are now also trying to move away from standard machine learning potentials to using many-body expansions. The reason is that many-body expansions, you can decompose your system energy into molecules and clusters. And this actually allows you to use a very high-level theory to describe all these energies, like coupled cluster. And you get fully converged training sets. You get high transferability. You don't need to always reparameterize all your interactions when you add a new species. So these we are currently developing for electrolytes and reactive systems and interfaces. So hopefully next time if there's a next time, then I will show some details about this. In general, we try to go beyond DFT also in this part. So we also have some recent works on using the random phase approximation, where we show that not only adsorption is significantly over-stabilized by DFT, but also, for example, the surface dissolution of atoms. And also, we have a lot of work on multi-scale modeling. So if anyone is interested, I'm happy to share this. So we develop multi-scale models for CO2 reduction. And probably the publication will also come up soon. OK, so with this, I think I'm perfectly in time. I thank you for your attention. And I'm sure there will be a couple of questions. Thanks.